Okay, thank you, Marcy, and thank you everyone for joining us. And I want to thank our guest speaker, Scott Brenneman, also for agreeing to do this webinar with me. We'll be talking about the primer for the use of cross-laminated timber. And this presentation is copyrighted by the American Wood Council. You should be receiving a link that tells you where you can download a PDF version of the presentation if you haven't done so already. I think Brian's providing that link. And it is an AIA presentation that we've also registered with AIA, as well as ICC and NCSCA. And in the PDF, you'll get the description and the learning objectives that you obtained when you registered for the presentation. And now we'll do our first poll to get everyone warmed up on how to use the poll. And Marcy?
Absolutely. So this one's very easy. Nobody gets it wrong. What is your profession? So just go ahead. If you're an architect or building designer, engineer, code official, builder, product manufacturer, or other. And remember, just vote within the poll question box, not in the question or chat box. And as usual, I give you about 30 seconds, 30 to 45 seconds, or when 80 to 85% have voted. So I've got about 85, 83% that have voted. I'm going to close, and then I share the poll. We've got about 75% engineers, 14% code officials, 5% architects, 5% other, and 1% builder product manufacturer. And I'm noticing I have a little typo for builder. I apologize about that. All right, so welcome to everyone here, and we're glad you're here. And I'm back to you, Michelle.
Great. Thank you. Thank you, Marcy, for the poll. And we've got a really good amount of engineers that are attendance. This you'll benefit quite greatly from Scott's presentation, as it'll get into real depth information related to designing for CLT later on. And so to give you an overview of the actual presentation, we're going to show you some buildings made out of CLT and give you an overview of CLT and why are designers and builders incorporating CLT into their projects. And then we'll go over the code path on which you can use to design CLT. And then later on in the presentation, about a quarter of the way through it, Scott Brenneman will take up the webinar and then go over overall structural system approaches, the designing of roof and floor using CLT, some considerations when they are used as a wall, and also horizontal diaphragms and vertical lateral resisting systems, where there are some limitations in the code, but there are options for you as designers to design using CLT and other prescribed lateral resisting systems. So when going into an overview of wood construction, a lot of times when we think of wood construction, we may think of stick framing, something that we're probably most familiar with, using different types of wood framing systems, sawn lumber, engineered wood products, etc., etc. But this presentation is going to be about cross-laminated timber. Now, this building is one of an iconic building in that it was, at the time of its completion in 2009, the tallest cross-laminated timber building in the world. And you can see this is looking down at the floor, where the floors, the walls, and the entire building of 8 stories over 1 level of concrete, the entire building above the concrete was made out of cross-laminated timber. So why are we looking at cross-laminated timber, and why is it that a lot of countries are incorporating wood into their buildings as a structure? Well, one reason is because of the challenges that we're having with climate change. And for those that aren't familiar with climate change, here's a little bit of background. This is just a high-level view of what the concept of climate change is and how important carbon dioxide is. So we have the world, picture of the world, and the sun projects solar radiation onto the world. And then some of that radiation goes back out as infrared radiation. But because of the atmosphere around, made up of natural or I have a trouble with that, so buildup of gases around the Earth, some of that infrared radiation does not get projected back out. It gets trapped in, and that helps us makes our world warm so that it can be habitable. Human beings can survive on the Earth because there is that warmth, the heat buildup. But what happens over time is that there's been a buildup of these greenhouse gases. And you can see over in the right-hand corner, one of the main contributors to that is carbon dioxide. And that's why when we talk about carbon or climate change and the buildup of greenhouse gases, we look at carbon dioxide and how we can reduce the level of carbon dioxide. Now, how does wood play a role in this? Well, we have, for example, a forest, and it can be unmanaged forest that can be grown with densely grown, or if it's not managed, it can be infested with bugs that then make it prone to wildfires, and then also the contributions of cars and factory emissions that release those carbon dioxide into the atmosphere. So when trees grow, they store carbon dioxide. They're about 49% carbon dioxide, but then when they decay and catch on fire through wildfires, that carbon dioxide is released into the atmosphere. But imagine a different scenario where we have a healthy forest, it's managed, and we store that carbon dioxide within the trees, and then those trees are made into wood products, or they can be made into bioenergy. Well, then those products are storing or sinking that carbon for long-term storage. So similarly, we have a house that, say, is roughly 2,400 square feet. That's about 32 metric cubic meters of structural wood, and that is storing 29 metric tons of carbon dioxide. And so your house is storing that amount of carbon dioxide, which is equivalent to about 5.7 passengers of annual emissions. Now, I mentioned, why is the world embracing this idea of utilizing wood? And that is because of that carbon storing capability of wood products. This is the example that we showed previously of the building in 24 Mary Grove in the UK that is storing roughly 300 metric tons of carbon dioxide. And that is about 21 years of building energy usage for this building. The other aspect related to wood structures is that it's 4 times less weight than concrete, and thus, from a seismic standpoint, seismic lateral loads is based on the weight of a building. That's less seismic load on a building. It also has less impact on the foundation, requiring less of a foundation for an equivalent concrete building. So we have a lot of other environmental characteristics, sustainable characteristics about wood structures. Now, even if you didn't believe in the whole climate change, we also, as good stewards of the earth, we want to be mindful of the resources that are available. And when we utilize wood products that come from a sustainably managed forest, that product and that resource is renewable, which is another sustainable aspect of wood. So what are we talking about today? We're talking about cross-laminated timber, and this is a picture of a cross-laminated timber. There was a patent in France dating back to 1985. It's been used in Europe since 1993 on projects all made out of CLT, and then increased significantly in the 2000s because of using it. The press technology and the manufacturing technology is improved, and since the early 2000s it's had an significantly increased in production and usage in Europe because of the green movement, because they want to have a less carbon footprint on their buildings. And then now there's over 500 CLT buildings in England alone. So we've seen this movement now across the pond in US and Canada, where the CLT is taking off and being used throughout the country and the nation, North America. So what is cross-laminated timber? This is an example that shows glue laminated timber, which is similar to cross-laminated timber in that they have layers of laminations. Glue laminated timber has all the laminations going in the major direction, so it can act beam-like, whereas cross-laminated timber is just that. The laminations on every other layer are cross-laminated, which provides dimensional stability and two-way action related to a panel action of the cross-laminated timber. It's manufactured very accurately using CNC technology. This is a picture of one facility that manufactured. Openings can be pre-cut into the panel, making it easy for installation of windows and doors. And here's a project that shows an example of the largest, I believe, residential project in the UK, Bridgeport House. Uh-oh, my PowerPoint stopped working. Uh-oh, sorry, my PowerPoint just rebooted. Okay, let me try and go from, okay, hang on, let me go to the one slide. My PowerPoint just rebooted. Let's see if that works. Oh, let me go completely out of it. Okay, let me go to that slide. I apologize, it just stopped and rebooted. Let's see if this works. Okay, let's see, hope that doesn't happen again. Now, okay, another project in North America is this Canadian project, the Abora, that I was fortunate enough to tour, made out of cross-laminated timber as well. And when it is completed, it'll be the largest residential project in North America when it's completed. And now we have the Brock Commons that'll be completed in 2017. I believe the structure is completed right now, and they're just doing the finishes. This is an 18-story cross-laminated timber, which is 17 stories of cross-laminated timber over one level of concrete podium. And then the first U.S. elementary school, which was completed in 2015. And this was prior to it being adopted into the International Building Code. And then we have the first hotel completed in 2016, prior to it being adopted into the 2015 and enforced in this state. And then in Portland, Oregon, another cross-laminated timber building was completed in 2016. I believe Scott's going to show a little bit more detail on this project. And then we have the framework building, which it's currently going through plan review, and it's anticipated to be the tallest wood building in the U.S. when completed at 12 stories. Now, what's the code path for utilizing cross-laminated timber? Well, when they were looking at changes for the 2015, some fire tests were provided. As you imagine, when any new product is getting introduced to be adopted into the code, there are two major considerations. One is related to fire and one is related to structural, and to be able to resist the loads. And the fire tests, American Wood Council did a fire test using ASTM E119. We sought to get 2 hours of fire resistance, and we obtained 3 hours and 6 minutes. And the only reason why the fire was stopped, because there was a breach right here where we had the drywall on each side of the panel. But this is where it flashed through, and it held 87,000 pounds still, even when the test was stopped. and the results was 3 hours and 6 minutes. So now it is currently adopted in the 2015 IBC under, there's definitions, it's also included in Chapter 23, and the standard for manufacturing cross-laminated timber, the ANSI APA PRG 320, is also adopted, incorporated into the code. It's adopted specifically under heavy timber construction, where the entire structure, exterior walls, the floors, the roof, and the interior partitions can all be made out of cross-laminated timber. Now, one other aspect is it also can be used under Type 3 construction, where some people confused that simply because it's under heavy timber, it cannot be used under Type 3 or Type 5. But what Type 3 construction states is that the exterior walls need to be of non-combustible material, but the interior building elements are of any material permitted by the code, and cross-laminated timber is permitted by the code. So, other than the exterior walls, the floor, the roof can be made out of, and interior partitions can all be out of cross-laminated timber. So that is true also for Type 5 construction, where the entire structure is permitted to be made out of any materials permitted by the code. So the entire structure under Type 5 construction can be made out of cross-laminated timber. Now, how do you design cross-laminated timber? Well, the 2015 references the 2015 NDS, and some of the provisions, we added a chapter for specifically to cross-laminated timber, which is Chapter 10. And there you will find references for the general design criteria, where you would go for design values, which is in the panels need to be manufactured in accordance to ANSI APA PRG 320. And whatever the products that are cross-laminated timber products under the code will need to be stamped. Here are the characteristics of the stamp, where they have the CLT grade qualified, the thickness, mill, similar to what you would see on a sawn lumber or wood product. The one thing I want to point out is that for those panels that are unbalanced layups, meaning that they're not uniformly through the depth of the, or a equal top and bottom uniform depth, equally balanced, similar to glulam, if the layup is not equally balanced or balanced, then the CLT will need to be stamped top. The minimum thicknesses, or the average, the thickness of the laminations is 5/8 to 2 inches and can be of sawn lumber or structural composite lumber, SCL, and the maximum thickness is 20 inches. And then the moisture content, which is similar to glue laminated timber, is in service is 16% moisture content. Now, the reference design values, which was alluding to previously, comes from the manufacturer or an evaluation report. And this shows you an example from the APA website for those manufacturers that manufacture CLT and are members of APA. They have a really good reference to the actual manufacturers, and they also provide a CLT product report, which is shown here, the product reports. There are other manufacturers out there, but these are the ones that are under the APA umbrella. When designing cross-laminated timber, we have applicable adjustment factors similar to what we have for other wood products that are shown here and shown in chapter, are referenced in Chapter 10. And also, for those that are looking for a quick, say you're in the schematic phase and you want to get just a rough reference of what your panel, what your cross-laminated timber cross-section might be, or size, or a specific grade, the ANSI APA PRG 320 is a really good resource for getting some design values. Here, this is the table that is the required characteristics of the test values in the PRG 320. And these are what the manufacturer will need to design, manufacture their panels to. So it's like a performance-based standard, manufacturing standard, as opposed to a regular recipe that needs to be done. So as long as they meet these test requirements, they can be graded under certain values like E1 or E2, et cetera, et cetera. Now the typical standard layups for roofs are roughly 3 layups, and then for floors they're typically about 5 plies for the floor system. There's also in this PRG 320 allowable design properties that you could use in your schematic phase of your project. And then this describes the actual CLT grades, different species throughout the depths of the actual CLT panel, different grades. And then there's also a handy table that provides some bending capacities also that can be used. But we encourage also working with manufacturers when you're in your designing of these types of buildings, because they can provide more in-depth information. So on our first poll, we have Marcy.
Right, sorry, excuse me, sorry about that. Let me see here. All right, CLT has the following connections. Is that, I'm sorry, am I in the right poll?
Has the following characteristics.
Yes, okay, and I am on, I'm sorry, I wasn't sure I was on the right poll. All right, laminations of 5/8 inches to 2-inch thick, laminations of sawn lumber or SCL, structural composite lumber, laminations all oriented in one direction, all of the above, or answers A and B. All right, and it looks like everybody is voting. That's awesome. I've got 59% voted. Just about maybe 10 more seconds. I need 10 more % of you to vote quickly. So, all right, I'm going to go ahead because we've got a lot to get through. So I'm going to go ahead and close and share. So we've got 86% say answers A and B, and then just a smattering, 6% say all of the above, 5% A, 3% B. And the real answer, Michelle, is?
And the real answer is A and B. And the laminations of 5/8 to 2 inches thick, the one that does not apply, well, and then there's sawn lumber and structural composite lumber, but the one that does not apply is the laminations all oriented in one direction. That would be similar to a glue laminated timber, where cross-laminated, the laminations are oriented 90 degrees to each other and every layer. Okay, so designing for cross-laminated timber, the connections, the NDS 2015 has been updated to include cross-laminated timber connections. And related to seismic design, this is something that Scott will get into in his presentation, but right now, currently under ASCE 7, under the 710, there are no provisions for cross-laminated timber. So there are options, performance-based design, et cetera, et cetera. There is research going on related to determining what the response modification coefficient is, but currently no prescriptive requirements or criteria for cross-laminated timber. But as I mentioned, Scott will get into what can designers do now using the current code and providing lateral systems for these type of buildings. The other aspect from a safety standpoint that we talk about is fire. And the NDS has incorporated cross-laminated timber into the requirements for calculating fire resistance. This is also adopted under the IBC under Chapter 7, Section 722 for calculating the fire resistance of an exposed wood member, which is similar to what is shown here for the glue laminated timber, but we're pretty much building into a sacrificial layer that will char and slow down the fire and prevent it from burning any further. You can calculate the actual thickness of that char, which is makes it predictable. We can predict how long it will take to char the thickness to allow you a certain amount of fire resistance. And again, this is adopted within the National Design Specifications under Chapter 16. The one thing to note is when designing for this type of fire resistance is there are applicable factors when checking your fire design, and that's under a separate table within Chapter 16. It's not the table that you would use under Chapter 10 for designing cross-laminated timber. And we also have a equation for determining the char, and that is one thing to note is for this char thickness or depth is that this is for laminations of equal thickness, and in the commentary of the NDS, if you have something other than that, there's some commentary to show how to adjust the equation for something other than equal thickness. And similar to the table in Chapter 16, this table applies only to those laminations of equal thicknesses. And I mentioned the ANSI APA PRG 320 performance specification or manufacturing specification. The one that is adopted in the current code 2015 IBC is the 2011 manufacturing specification. And within that specification for the adhesives, it references the adhesives that are used for glue laminated timber. So there is a history of some use within glue laminated timber members that are specified under the CLT manufacturing specification. There is a 2012 specification out there which is not adopted under the IBC, but the only major difference between the two is that there were some clerical revisions to the 2012, but basically they're overall the same. Now, one thing to note, if you're calculating the fire resistance of an exposed wood member, we want to make sure that not only are we calculating the fire resistance of that wood member, but we have to look at it as a system. So the cross-laminated timber, wherever it spans to and whatever it's supporting, the connections of that cross-laminated timber to the wall or whatever need to have the same amount of fire resistance that was calculated for that cross-laminated timber. So for example, if you calculated it for 1 hour fire resistance, the connection of that member to the whatever supporting it, that connection needs to be provided with the same amount of fire resistance. And to provide that fire resistance, one could use wood or gypsum to provide that fire resistance. Now there's a technical report number 10 that's available on the AWC website that also has design examples on calculating for fire resistance, and that's a free download from our website. Now the last item that I'm going to go over is that in order, there was some there was a demonstration fire that was performed by AWC, and it was back in 2015 that this occurred. And the idea was to conduct 2 demonstration fire tests of typical residential occupancy, and it occurred in Southwest Research Institute in San Antonio, Texas. And it was to show how protected cross-laminated timber would fare under a compartment fire test, estimated to be about, let's see, 95% of tile of the, excuse me, modern residential fuel content loading. You can see on the right all the amount of furniture, that's the fuel when the fire is started. And the cross-laminated timbers, the cross-laminated members that were used were manufactured using ANSI APA PRG 320. There was about 5 laminations thick. The 2 tests, one had a nail laminated timber ceiling, and the second one had a cross-laminated timber ceiling, and had a load of 40 pounds per square feet. And they all were covered with 5/8, 2 layers of 5/8 types X, and you can see a picture of the fire being burned. But what we want to point out here is this figure shows that the heat release rate, we have time on the horizontal axis, heat release on the vertical axis. It shows that the heat release rate grew rapidly to about 5 mega MW in about 4 minutes. So you can see here, megawatts. And then over time, the heat release obviously decreased due to the not burning of all the fuel. And what this shows is that it's about 2,000. So we have, again, time on the horizontal axis, temperature now on the vertical axis, time on the horizontal axis, and at the heat rose to about 2,000 Fahrenheit in about 4 minutes, and then dropping to about 700 at about 30 minutes. So, and this drop has to do with the fuel being all burned up and no fuel left. But you can see that the first 15 minutes far exceeded what was required for the ASTM E199 test. So you can see after the 3-hour test, and they did run it for 3 hours, but you can see that there was very little damage to the cross-laminated timber. The picture on the left shows a bookcase that had fuel. I think they were old passcodes that were used to burn there, but very little damage to the cross-laminated timber. If you'd like more information, we do have a webinar on this, a recorded webinar to provide more feedback on this. So rounding off, I wanted to let you know that some of you may not be aware of this, but there's an effort, there's an ad hoc committee from ICC to look at tall wood construction and buildings, and AWC has a web page that gives you the current information on what is going on through this effort, which is awc.org/tallwood. And resources are available. The NDS and Wind and Seismic, our publications are available for free in a PDF version. It does not include the commentary, but other than that, it's available for free from our website. There are articles that are available. If you look at our website for what's changed, there's this green icon that if you click on that, that'll tell you what's changed from the previous version. And now I'll hand it off to Scott, who will take it from here. Make him presenter.
All right, thank you, Michelle. And Michelle, thank you, Michelle, for covering a lot of material pretty quickly. And I hope we'll have time now to delve into some of the details on CLT. So first, I'm going to take a step back and talk about structural systems and what kind of buildings, or what do the buildings look like that use CLT in them. That's kind of maybe CLT is part of a larger class of products called mass timber. So we're kind of going to look at mass timber structural systems and what they may look like. This is my pretty outline in an org chart and versus bullet points. So really we're going to talk about gravity systems and then lateral force resisting systems. And then looking at gravity systems, there are several different styles we're going to cover. Post and beam kind of traditional styles maybe you're used to seeing in the old warehouses, two-way panel decks, as well as what we call a honeycomb system. And as we walk through these, you'll see pictures of some of the projects that Michelle showed, but I will be pointing out some particulars about the structural systems. So here's the Albina Yard project, and this is a kind of a classic example, if you will, of the post and beam, or a modern post and beam project. And in that, we kind of see, a glulam grid supporting the floor. So in this case, we have beams and girders running in two different directions, and those are supported upon glulam columns. But then spanning between the beams of the floor framing system is our CLT panel. I believe in this case, spanning around, well, maybe I shouldn't say, I don't remember what the actual span is on this one. But this is a 4-story CLT project, which is complete, and I had the pleasure of touring the building a couple weeks ago in Portland, and it's a very nice office building. But this is kind of a good post and beam example using a CLT floor system. Other post and beam projects, this is a Hudson building, another office building in Portland, and here we see again a framework of beams in the floor system supported by columns. And as we go through this, you'll see different connection styles. This one actually happens to be nail laminated timber instead of CLT, but this could easily be a CLT floor deck as well. Another post and beam example with a kind of a different architectural feel is the T3 project that is nearing completion in Minneapolis. Here again, we primarily see a one direction frame of beams within the floor system supported on our columns. There is a perimeter beam in this case. And here at the connection areas, you see really a very clean connection with most of the hardware all hidden within the wood itself. So, but again, just variations of the post and beam structural system, all of which could be supporting CLT floors and roofs. This is the Bullet Center project in Seattle. Again, we have glulam beams, glulam columns. This one has a nice architectural feel that they did not require a perimeter beam, and so they were able to take the windows all the way up to the floor deck above. This project completed, opened up in 2013 before really CLT manufacturing took off in the US, and so they were using a nail laminated timber system for the floor system. But again, just kind of the post and beam system can be used with CLT and the other mass timber products. It's probably the most popular system we're seeing using CLT today, particularly in these office projects where they're leaving the CLT exposed to create a nice warm ceiling space. These work up to certain spans, as Michelle mentioned, maybe a 5-ply floor panel is a common floor panel thickness for CLT, and that can span, depending upon the actual grade and everything, maybe 15, 17 feet in that range. But if you want to go longer, people are starting to innovate and come up with different systems. For example, for a long span system, you can use kind of a concrete topping on top of a CLT panel to create what was called a timber concrete composite, where concrete is great in compression, as we know, and wood's pretty good in tension. It kind of is a leave-in-place formwork, but then it becomes a composite floor system that can be something worth considering for a longer floor spans, above kind of the 17-foot range. There's a lot of detailing considerations that need to be taken to make sure this is done right, but it's just one of those variety of solutions that are available there in the CLT world. What that might look like, there are different ways to create the composite action. Here's some pictures of a project up in Vancouver where they use these perforated steel plates epoxied into the CLT and then created kind of like almost a continuous shear key between the CLT and the concrete that would be poured in place on site on top of this insulation layer. Other systems that have been using CLT for the floor systems, the Wood Innovation Design Center, also in British Columbia, our Canadian neighbors to the north have really been leading the charge on some of the technologies related to these mass timber products. This is a great project that's nearly 100 feet tall, that's been completed and opened a couple years. But looking at the structural system for this, it kind of looks like a post and beam, but you look at the floor system and you see what is both these kind of staggered CLT panels with some sort of architectural infill. And something's a little different about this one. And what is different about this one is that it has kind of a 2-layer CLT floor deck where you have 2 different layers of CLT all spanning in one direction together, but they're staggered to create kind of chases on the top and bottom for systems, so that we have a chase for electrical systems in the floor, and then we have a kind of a chase for fires and fire sprinkler lines and lighting and electrical in the ceiling, and this kind of staggered system where there's kind of a lot of connection at this deeper section to kind of create deeper ribs, if you will, that span in that direction. So just kind of another creative application of CLT in a floor system used in conjunction with the post and beam framework. Moving on to our next gravity framing style is the 2-way deck. Michelle showed you a picture of the Brock Commons project, 18 stories, 17 stories of wood over a 1-story concrete podium. This is a project that's definitely an alternate means. In British Columbia, they don't allow an 18-story tall wood building, but they went through an alternate means process through their jurisdictions to justify this building. But what actually is interesting from our structural gravity load perspective is that it uses a two-way floor deck, meaning that it uses the CLT to span in both the long direction and the short direction of the panel and have that supported just on columns at the corners and interior points of those panels. These other little framing members you see here between the columns are really just spacers that will be taken down, that were taken down after the CLT panels were put into place. So this is kind of really using that two-way spanning capability to create a beamless floor system. So it's kind of an interesting idea. But where we see actually this two-way spanning capability used the most to date in CLT systems is creating kind of a beamless cantilever roof. This project in Chicago actually took that to an extreme where it's a pavilion where you have really a CLT roof supported on isolated columns with no other framing at all. But you can imagine this being kind of at the corner of a building where you have a roof deck, a roof spanning off the corner with two directions at the corner with no supporting beams. Here's another picture of that really attractive pavilion project right on the lake in Chicago. In this case, they actually took 3-ply panels and has 2 layers of 3-ply panels. So they took this and alternated the directions of those panels. So we have 3-ply panels. Each panel has a strong direction, and they took 2 of those panels and had one set of panels running left to right, if you will, and the other set of panels running front to back to create kind of this composite 6-ply system that's then screwed together to create the two-way spanning strength in the roof system. So the honeycomb project, the honeycomb style is kind of, well, it's kind of a nice nickname for what we see in buildings where we're using CLT floors supported on CLT walls. Really kind of beamless systems, if you will, but this style makes sense for those projects where you have on the base. It had to pass blast criteria and progressive collapse criteria, and really the design of this building really took advantage of the CLT strength in the walls to meet their criteria they needed for blast resistance and progressive collapse resistance. But really good example of the kind of using those bearing walls supporting floors. This large number of people here on the roof was actually there to observe the last panel to be put in place. The actual crew that erected the frame was about 6 people, as a framing crew, and that was a real good project. And I think Lend-Lease, who is the developer and builder of this, is looking to replicate this around the country. So my first poll question. I'm going to read the question and then I'll change it over. Marcy can take over to let you take the poll. Which of the following is not a common framing style used with CLT? A, post and beam framing. B, two-way CLT panel spans. C, 3D space truss. Or D, CLT floors supported on CLT walls. Which is the one not commonly used?
All right, let's go. Remember to vote within the poll box. Every once in a while I see a little answer pop up in the question box, so I just want you to remember to answer within the poll box. So, all right, I've got about 30 seconds there, and 78% voted, so if we can get that 80% threshold. All right, 45 seconds, so I'm going to close and share the answers. So we've got 94% say that 3D space trusses are not a common framing style used with CLT, and then just 2% each said the other answers. So I'm going to go with Scott, that I think that they all have the right answer.
It sounds like we've been paying attention. That's good.
Awesome.
And I will attempt to slow down my speaking a little bit, because I heard that you may have lost audio for a couple seconds or so. Okay, so I think it's, so yes, C, 3D space truss is not a common framing style used with CLT. Now, I don't say it couldn't happen, but, you know, common one. Excuse me. So one of the questions that often comes up is, well, who are the manufacturers of CLT? As Michelle covered, the IBC references the ANSI APA PRG 320 standard as the code adopted path of CLT. So I have listed on the screen 4 manufacturers who have their products certified to that standard. There are other manufacturers in North America and around the world, but these are the ones who have met the requirements of the direct code reference to the PRG 320 standard. You know, two out west, North America and Canada, and 2 out east, if you will. Well, and actually, that's not true. 3 more out west and 1 in the east. So I'm going to dig a little deeper into the structural design of CLT and using CLT. You know, once you kind of get your head around the simplicity of CLT and how it's kind of just glue lam with the lamination spanning in 2 different directions, you start to think about it, and as an engineered product, or a product you use for engineering, you know, this is a non-homogeneous anisotropic material, so it has different strength properties in different directions and has different properties through the thickness of the panel. You might say this gets pretty complicated to design with, but actually that's not true. The standards and the design methods have really taken care of a lot of that for you. So, for example, if we're just looking at CLT as a floor or roof application under a bending load, what is that? How would you check that bending capacity of the panel? You could kind of look into the stresses through the section of the panel, and let's say we're applying the moment on the strong direction of the panel. So we have laminations on the exterior in the strong direction, and an interior middle one in the strong direction, and then there's transverse layers which are not nearly as strong. If you looked at the stress distribution through that depth, you know, you kind of get this jagged distribution like that. But if you just kind of visualize that you're ignoring the layers in the transverse direction, it still really is just kind of a rectangular distribution through the depth. But luckily, if we took that applied bending moment, we are given by the manufacturers a bending capacity. So the applied bending moment, or M sub B, needs to be less than our bending capacity. You know, the words FB, S effective. You know, FB kind of looks like an allowable stress for bending, and S effective is the section modulus. But in reality, you're given this as a composite property, FB, S effective. And then you modify that depth, or sorry, that section capacity using the adjustment factors that you find in Chapter 10 of the NDS. So in reality, that comes out as we have our FBS effective, our bending capacity that is provided by the manufacturer or the PRG 320 standard. And then we have our modification factors from the NDS 2015. Now, if you look at the scope of the PRG 320, it's for typically for interior applications. So C sub M for moisture content and C sub T for temperature are commonly going to be 1.0. C sub L is a bending component for like narrow beams, and if you're talking about a wide panel, that's commonly going to be 1.0. So for almost all kind of floor or roof applications within a building, that's going to really resolve in, you know, our time duration adjustment factor times the capacity, bending capacity given to us by the manufacturer. So it's a pretty simple check. Our applied bending moment needs to be less than the provided bending capacity times the duration adjustment factor. So to make an example based on that, we're going to look at this basic 15-foot span example in several different ways. But if we take a 15-foot floor span, we apply kind of typical loading of 40 PSF live load and 40 PSF dead load on that, and assume just one-way spanning behavior of the CLT in the major strength direction of the CLT. We can go through that, use our normal beam equations, and come up with the the applied or the demand for bending moment at the center of the beam or the CLT at 2,500 pounds per pound-feet per feet. So we're kind of doing an analysis on a 12-inch wide or 1 foot wide strip, if you will, of the CLT. Now, we take that and say, well, we need something that has that capacity in it. And we're going to look at the standard grades and standard sections in the PRG 320 and say, well, this is a floor system. Let's start with a 5-ply. And let's look at V2 grade, for example, because say we're trying to use that grade as our locally sourced CLT and pick something that has that capacity. Our major strength capacity, this FB S effective, and 0 means in the major strength direction is in this column. We're going to go down and find something that's greater than that 2,500 and change. And looking at the V2 grade, that would be this 5-ply 6 and 7/8 inch thick panel, and that one would satisfy our bending demands. So that's a pretty straightforward check. You know, what is the applied bending load? And here we go through and find the capacity of the different sections. Since we were using dead and live, our C sub D factor is 1.0, so we don't have to do adjustment factors for that. So I just talked us through this next slide already, where we grabbed our 4675 pound-feet per feet of capacity, multiplied it by the C sub D of 1.0, and that's greater than our 2560 pound-feet per foot of demand. Our flexural strength is okay for that check. For shear strength, there's something similar. You know, we have a applied planar shear load, sometimes called a planar load, or sometimes called the rolling shear, which is the demand needs to be less than the capacity. And again, you know, we have a term that looks like it's an allowable stress term. F sub S I B Q effective is the shear strength of the panel. And you can get into what does the shear stress distribution look like. But in the end, you know, we really need our applied shear to be less than the shear strength of the section. Now, that shear strength of the section can be written out in that long term, or if you find and look at the manufacturer's product reports, you'll find that shear strength just reported as V sub S. So instead of carrying around this long term of different letters, really a V sub S is our shear strength of the section. Something to note here is that in the NDS 2015, we don't have a time adjustment factor or time duration of load factor on the shear strength. So we don't have a C sub D factor for our shear strength. But again, our modification factors for moisture and temperature in an interior application are typically going to be 1.0. So our applied shear needs to be less than our shear strength. Very simple check. We're going to get that shear strength from the product reports or from the manufacturers. Something to note about my slides here is typically the values that are presented in red are the values that will be given to you directly from the manufacturers or the product standard. So what about stiffness? You know, if we need to do a deflection check, we need a shear stiffness. And if you go and read the CLT handbook, which is a resource available for free that you can download, that was published, I think, in early 2013, so it's a couple years old. You'll get into there and there'll be different, there's a chapter in the structural section on CLT modeling, and you'll find lots of equations, kind of like the ones you see on the screen now, where you calculate the shear stiffness, the flexural stiffness, you calculate the S effective, you calculate the shear term. So you have all these equations in there, but really what you need as a designer typically is the EI effective. And luckily, that is a value that the manufacturers are calculating and checking via testing for you. So there's an EI effective, which is the flexural stiffness, and a GA effective, which is the shear stiffness. Because of the cross-laminated nature of CLT, the actual shear stiffness is more significant than you would think of for a solid sawn beam, for example, in that those cross-laminations are aligned in a weak direction so that the shear deformations are higher and the shear stiffness is lower than there would be of a similar section of solid lumber with all the fibers running in one direction. So when you're getting into deflection calculations for CLT, for shorter spans in particular, you need to pay attention to shear deflections more than you would necessarily for solid sawn. If we're talking about long spans, our typical engineering analysis applies where shear really doesn't have much of an effect. But an important thing to note about all these different equations and how you derive the different section properties, they're really important for the manufacturers to develop the design properties of their CLT sections, or if you're really going out on the edge and you're trying to develop a custom section for yourself, this could be something you could get into, but it's really not important for you to be using the standard sections because the section properties will be published by the manufacturer. And those published values from the manufacturer, if they've gone through the PRG 320 certification process, have been verified through testing. So if we take a step back now and look at our panel, and we've picked a section, we've picked a grade, whether it's in the PRG 320 or something that's specific to a manufacturer, the major section properties that you're going to be given are the 8 you see here: the flexural strength, the flexural stiffness, the shear strength, and the shear stiffness in the 2 different directions. So, given that, one of the checks we need to do as designers, particularly if we're looking at floor systems, is deflection calculations, deflection checks. L over 360, L over 240, whatever our criteria is that we want to use to check the deflections of the floor system. One approach is, and it would be an approach that would be taken like on the Brock Commons or on those roof systems where you have the cantilever out in 2 different directions, is to really look at the 2-way plate action of the CLT and then calculate the deflections based upon that 2-way plate behavior. So you have all the stiffnesses that you need, and you might need to go into a FEM software that can do that plate analysis and apply a model of that 2-way spanning behavior. If you go through here and you look at, there's a shape factor of the 5/6 that is on the shear stiffness, and this is really the shape factor for wood shear deflections that you'll find in many documents, such as the Forest Products Lab wood is an engineered material. So if you had a round wood material, they would have a different shape factor, but the 5/6 is our standard shape factor for rectangular sections under shear deformations. Similar, you can go into, if you don't have a 2-way plate action system, if you have panels just spanning between beams or spanning between walls, where you're really not relying on that 2-way behavior very strongly, you can really just do a simple 1-way beam analysis of the panels. This could be for multiple spans. If a 5-ply panel, for example, can span around 15 feet, but you can get a panel that's 30 or 45 feet long, it may be advantageous to have a multi-span panel over multiple spans of beams. And if you're doing your deflection checks, you could definitely take advantage of that multi-span case and do the beam analysis over the multiple spans. Or if you have cantilevers, this is kind of a general approach you can take to analyze the deflections of the project or of the member for just using a beam strip analysis. So going back to our 16-foot example and our 80 pounds of dead and live load, let's go back and check our deflections for that one. So we can get our flexural stiffness and our shear stiffness from, in this case, the PRG 320 values, and plug them into a beam deflection equation, including shear deformations explicitly, and walk through those calculations. I don't have all the details shown, but basically you get about 0.16 inches of flexural deformation, about 0.02, very small, shear deformation at the middle, so a resulting deflection at the middle of 0.18 inches. So in this case, it's almost like an L over 1,000 deflection for this 5-ply panel spanning 16 feet in a kind of a common floor application. Now, one of a convenience that has been developed for CLT and other products is what's called an apparent stiffness. So if you think about this deflection equation with kind of both our flexural term and our shear term in it and say, well, what would be the equivalent EI that would give you the exact same deflection? So if we take our beam equation with both our flexure and our shear, and let's just suppose that we just lump all the deflection into flexural behavior and look at the equation for deflection to just flexure, this would be the simpler equation. And if we equate these two equations and solve for EI apparent, we get a result that kind of looks like this, where the EI apparent is a function of the flexural stiffness, the shear stiffness, and the span length. So this is the kind of the background of the EI apparent that you see used in different CLT design methods. So there's an EI apparent that is in the NDS 2015 when you're looking at the a column capacity or a wall under bearing load on the end of a wall. It uses an EI apparent. And there's some other places that use this EI apparent. So if you come across it, that's just what EI apparent and how it differs from the EI effective. It's included a measure of the shear stiffness into an apparent flexural stiffness. There's a couple different forms of the EI apparent. There's a form that you find in the body of the NDS 2015 shown here on the right, and there's a form shown in the commentary of the NDS 2015, as well as the form that's shown in the CLT handbook. They give you the same answer, they're the same result, they're just algebraically manipulated in different ways. But if you go back to my note about how the different values in red are the values provided by the designer or provided by the manufacturers for their sections, you'll see that the one in the NDS commentary is a little more useful to use, and you don't have to go through intermediate calculations to use the one in the NDS body. But again, they're the same result. It's just kind of like you see different equations. They're kind of just algebraically equivalent. Another important thing to note about is that the apparent flexural stiffness depends upon the span length. Since the apparent stiffness is accounting for shear deformations, and we know shear deformations are more significant at shorter spans than they are at longer spans relative to the flexural deformations, that this EI apparent actually varies on the length of the span. Another important component of our deflection calculations is the creep term, the creep factor for long-term loading. We have the typical equation in the NDS for our creep term for long-term loading, and for CLT, the KCR is a value of 2.0. So you take the immediate deflection due to long-term loading and multiply that by 2 to get the eventual deflection after the creep has kind of occurred over that deformation, from that loading. So an important thing about floor design CLT is like almost every other floor system out there, that often what really governs what is an acceptable floor design, not acceptable by code, but acceptable by performance, is floor vibration. So if it's an office or a residence, really what kind of drives a lot of the sizing of members is how bouncy is the floor, and is that acceptable, is it acceptably stiff for the occupants. So this is, this is the same for steel framing, this is the same for light framing, light frame wood, where floor vibration often really governs our floor design and really drives the sizes rather than meeting code required strength. It's meeting this occupant comfort criteria. There are several different approaches you can take for floor vibration design for CLT. One approach is presented in the CLT handbook, and really they've looked at tested data and came up with kind of a simple recommendation on what is an acceptable span for a CLT panel. So really the EI apparent, is that EI apparent flexural stiffness term, and the rest of this is just the density of the CLT, the cross-sectional area, and the length spanned, and that's how you can estimate the frequency. And then there's a relationship that they've derived to come up with what is a reasonable behavior out of the CLT panel. So given a panel, the maximum span L that kind of meets this criteria is found by using this equation. So this is kind of a good way to start floor design, is looking at this maximum span for reasonable behavior of CLT panels. If you look at this equation, it has the EI apparent, and the EI apparent depends on L. So if you actually want to run through the calculations, it's somewhat of an iterative solution where you assume an L, you go through, calculate the EI apparent, calculate the maximum span L, and then kind of continue until they kind of converge on a single value. But the beauty of this approach is its simplicity, that the only thing in this equation is properties of the panel itself. So really what happens is, given a section of CLT, the manufacturers can go through this calculation and say, this is the maximum span recommended by the CLT handbook for acceptable or reasonable floor vibration behavior. It's somewhat of a simple approach, but it also can be done for the section and isn't particularly dependent upon the project design particulars. So for example, if we go back to our 16-foot example that we've gone through, our V2 grade 5-ply CLT, which is 6 and 7/8 inches thick, the L max for this recommended limit is 16.7 feet. You know, fantastic. Our 16-foot span is less than this L max. We're good. So if we think about that 16-foot span, we had ample capacity for strength checks. You know, we had an L over 1,000 approximately for our deflection checks, but really this floor vibration criteria for occupant comfort is what governed that span, and the recommended max of the CLT handbook is 16.7 feet, and our span was 16 feet. So we're good to go on that respect. Some disadvantages of this approach is that it doesn't take advantages of other stiffening effects. Like if you have a non-structural topping slab for strength, actually that non-structural topping slab actually stiffens up the floor system, and because floor vibration is not a code minimum load requirement, it's really a performance observed by the occupants criteria, you know, you can take advantage in some cases of that topping slab to stiffen up the system. It also doesn't take advantage of those multiple spans. So if we have that 45-foot panel over 15-foot spans of beams, we haven't taken advantage of that stiffening effects of the multi-spans. And another disadvantage of this approach, if you're looking for long spans, this is actually a fairly inefficient way to keep the natural frequency above 9 hertz, which was also recommended by the CLT handbook. So if you're really pushing the envelope and really trying to sharpen the pencil, you can take other approaches to floor vibration design. You have to go back, you know, really it's you know, we're back to first principles, if you will, as engineers and designers. Is like, well, what's another acceptance criteria we can use for our floor vibration, and then how do we model our floor system to verify against that acceptance criteria? You know, one common acceptance criteria or design approach, if you will, for floor vibration that many U.S. engineers are familiar with is the AISC Design Guide 11. You know, there's many different chapters in AISC Design Guide 11, and some of them deal with modeling of framing systems, and obviously those are targeted towards steel, and some of them are really what is the approach you would take to estimate the dynamic behavior and what is an acceptable acceptance criteria of that dynamic behavior. So how you could use this for CLT floor design is really looking at the acceptance criteria side, not the modeling side, and you know, and say, well, what's an acceptable acceptance criteria? You know, for example, you know, if you're doing a residential area, maybe this 16,000 micro inch per second, which is a MIPS, which is a measure of velocity. 16,000 MIPS is acceptable in kind of living areas, and 8,000 MIPS is acceptable in the sleeping areas. So we have a lower criteria in a sleeping area because you're more sensitive to accelerations when you're laying in bed and somebody's walking by in the room next door. So this is a way to come up with what alternate acceptance criteria, if you will, then you apply, you know, to the CLT framing system. So it's not, you're not going to, you know, obviously AISC Design Guide 11 is not going to give you dynamic modeling advice, but it can give you an alternate acceptance criteria where you've modeled the system to take care of multi-spans and topping slabs or wherever else you want to really sharpen the pencil. You know, another alternate vibration criteria is the ATC Design Guide 1, which again is kind of really not specific to CLT. It's a publication from 1999, but it really talks about acceptance criteria for floor vibration. There are ISO standards out there that address the same thing on the acceptance criteria. So if you have further questions on that, that's kind of thing you could try to contact me or somewhere else later to give you pointers on where to go. So what do these systems look like in terms of detailing? Well, you know, if we're talking about floor and roof systems, there's a couple different styles of connections. Kind of the most common one, if you will, the most economical, is really just a surface spline where you have two panels that come together, and the manufacturer and fabricator of the CLT may route a little groove in that, and then in the field after those panels are placed, then you drop in a piece of plywood or structural composite lumber that really is screwed or nailed down to those two different panels to hold them together. You know, another approach is what's called a half lap. So instead of that one spline that gets dropped on the top, panels can overlap each other with a screw coming down through the panels and tying them together this way. The half lap gives a mechanism to share vertical loads a little more than the surface spline. And the surface spline really is the primary mechanism to share, you know, shear loads or diaphragm loads. But also in the surface spline, you can actually come through with long screws and run through horizontally here to create more of a vertical load connection between those panels as well. You know, really these things really come together quite simply. The surface spline can also use nails as well as screws. So what might that look like in the field? You know, this is a pictures, I think, of that school that Michelle mentioned that was the first school in the U.S. to use CLT. So here we see the two different panels with the spline resting between them, and in this case, I believe they're nails stitching those together along the length of that panel-to-panel connection at the floor system. Okay, so if we're talking about the honeycomb system or a bearing wall system, what might these look like? Again, you know, in a kind of a low to mid-rise building, you might have a CLT panel resting on the wall, and then the next CLT wall dropped on top of it. So really, you know, this is all just kind of sitting together. You know, gravity holds this together, but you really want to connect it better than that. So we're putting long screws through the panel down into the wall below, other long screws from the panel of the roof, the wall panel into the floor panel, or there can be different, you know, angle brackets which are screwed or nailed or bolted from one to the other. There's several different detailing styles that can be used, but it's really, you know, fairly simple fastening equipment to put these together. You know, we're talking screws or nails with light gauge clips. So something very familiar to, let's say, a light frame contractor. You know, really, you know, quiet equipment and fast equipment to put these together. So you've heard me mention several of these, you know, screw systems. You know, if you know, we have our commodity screws in the marketplace, and, you know, our lag screws and things like that. We have our commodity nails, but these kind of fairly new, well, they kind of have been developed over the years, primarily in Europe, just like CLT was developed in Europe. These self-tapping proprietary screws are really a very powerful connecting device on CLT products. There's different manufacturers of these out there. You know, many of them have ICC reports for their products, but they're really something. If you're looking at CLT systems, it should be something in your quiver of tools to use in your connection details. Okay, I have another poll question here to break things up. True or false? CLT deflections can only be calculated using a simply supported beam strip analysis.
All right, that's pretty straightforward, so I'm going to let y'all go. And hopefully this will be quick and easy for you. And again, remember to vote within the poll box. So I don't know if it's blue for you all, it's blue for me, so go ahead and click in that box to vote. I've got 73% of you have voted in 30 seconds, so I'm going to give you another 10 seconds. Let's get 80% of you to vote. Remember that if you get all the answers correct, I pick from those of you that get all the answers correct to win a free publication. So, all right, I'm going to go ahead and close and see. I've got 80% say false and 20% say true. And Scott, the real answer is?
Well, the real answer is false. Now, maybe, you know, using a beam strip analysis is the simplest way to do a deflection calculation of CLT. So that's kind of maybe a little tricky there in terms of it's definitely the most common way to do it and the simple way to do it. But if you're looking at these two-way plate actions at the cantilevered corner of a roof or two-way floor spanning like the Brock Commons, you really want to look at kind of a two-way analysis. Or if you're looking at multi-span floors where the panels span over multiple beams or multiple walls, you can really take advantage of the multi-span strength or stiffness of the panels and do a kind of a non-simple supported, a complicated supported strip analysis. So you know, it's definitely something it's very commonly done, but it's not the only way it can be done. Okay, so that's gravity systems. We're going to move on to lateral systems, and all that entails. Lateral systems, what's our wind force resisting and our seismic force resisting systems, and all of that entails. So first off, you know, CLT itself is a very strong panel for in-plane capacities. This is some values from a manufacturer's design guide where they're given the in-plane shear strength of their panels themselves. Now right now you won't find these capacities in the PRG 320 standard. These are things, the testing of the in-plane shear strength has something that's been standardized and kind of created a more uniform testing protocol since 2012 when that standard was created. And the standards are being updated right now, literally this year, to include the new standard testing methods for in-plane shear capacity. So you won't find it right now in the PRG 320 standard, but the actual in-plane shear capacity methods and testing of that capacity is being standardized. However, if we look at these capacity, if we look at the SLT3, which is a 3-ply panel, you know, we're getting 2,900 pounds per foot of shear strength. If you look at our 5-ply panel, we're getting 5,800 pounds per foot. So 5.8 kips per foot of strength of the panel itself. So the actual panel itself is very strong in plane. And it's important to note and think about that when you do our design of our lateral force resisting systems. But it shouldn't be that strange to us. If we're used to doing wood structural panels, shear walls, or diaphragms, we know the strength of those diaphragms is really governed typically by the connections or the nail spacing of the panels. So if we took a wood structural panel shear wall and we have nailing around the edge, which is 6 inches on center, 4 inches on center, 2 inches on center, that nail spacing is what's really governing and determining the strength of that system for shear loads. That's really the same case for CLT as well, where the shear capacity for a diaphragm or a shear wall is really dependent upon the connections at the edges of those panels. So that's really what you need to think about. We should check the capacities of the panels themselves when we're doing some sort of lateral force resisting system, but really understand that the strength of the system is going to really depend upon the connections. Luckily, for our commodity-based connectors, the NDS NDS 2015 has included now provisions for connectors and fasteners in CLT. So our nails and our commodity lag screws and etc. are covered under the NDS, and this is how we could go calculate the strength of those fasteners in CLT, as well as the proprietary manufacturers of screws have tested and published design capacities that by and large follow the same pattern and requirements of the NDS. It's just they've kind of expanded those for the hardware that they provide. If we think about seismic design in particular, we don't have CLT seismic force resisting systems adopted in our standards right now. So ASC 710 and our special design provisions for wind and seismic is where we go to find accepted seismic systems and where we go to design our accepted wood systems. CLT force resisting systems are not yet addressed in those documents. So if we're doing a seismic design using CLT, there's several different approaches we can do. And I'm going to cover a couple of those. But this project here, while it doesn't have CLT, it has a kind of a tongue and groove floor system over a post and beam frame, but you can imagine that being CLT as well. In this project, 4 stories, type 5 construction, what they used as their vertical seismic force resisting system is a light frame wood structural panel shear wall. Perfectly acceptable to mix and match. The Albina Yard project that Michelle mentioned and I had pictures of earlier did the same thing. So this actually is a CLT floor, below and above this picture, and they used, again, wood structural panel shear walls as their vertical seismic force resisting system in this. This actually had most of the lateral resistance at the cores, and so these end up being double-sided, core walls or shear walls. Although, if you're doing a CLT floor system and you don't have places in your floor plan for shear walls, you can combine a CLT floor and a glue-lam frame system with a steel moment frame, as in this project example. The Bullet Center project in Seattle used this all wood framework for gravity loads on the upper 4 stories, and could use that with a steel brace frame system. So really, as you start looking at and using CLT for floor systems or roof systems or in other components, and you're in a seismic design position, you don't have to be, there's not just one solution for a vertical seismic force resisting system. You can really pick from what you have available in the codes today to use with that framing system. The T3 project, which is a 6-story, well, it's a 7 stories total, it's a 6-story wood frame over 1-story concrete in Minneapolis. They chose to use a concrete core as their horizontal force resisting system that's in the middle of the building. That said, there are definitely designs and projects using CLT shear walls even in seismic locations. But of course, the question always regarding seismic design with CLT shear walls is, what's the R value I can use? So reality, that's research in progress. If you are somebody who tracks, kind of the seismic design standards, over the past, 10 years really, the seismic and structural engineering community has really elevated the process, if you will, to validate new shear wall systems, new vertical seismic force resisting systems, and that's all contained in the standard, the FEMA P695. So there's an ongoing multi-year project led by John Vandalent at Colorado State University undergoing this process, which we're getting near the end of, that we hope will define a CLT shear wall system and then have the R value and C sub D and omega naught value resulting from the 695 process. Now, when they complete their research here within a year, it's not going to be in ASC 710, it's not going to be in ASC 716, which is pretty much already written and not published yet. So we're not going to have that code adopted seismic shear wall system for a while, but when this research is done, it may be an advantageous route to do an alternate means for a CLT shear wall system. There are jurisdictions and places around the country which kind of have moved, have kind of taken a step forward while we're still waiting for that research. So for example, the state of Oregon has a statewide alternate method adopting CLT into their 2014 code, and then also adopting a shear wall system for it. So in the Oregon statewide adoption of CLT, they went out and said, well, for now, while we're waiting on this research to be completed, we will approve the use of an R of 2 for CLT shear walls, which by everybody involved really is a conservative value, and the real values we will be somewhat higher than that, as we hope as designers. So for the state of Oregon, they have this statewide adopted kind of alternate already approved. And such kind of conservative designs have been used through alternate means at other places around the country. I don't have any finished pictures of this project in this presentation, but this is a UMass Amherst building that has low seismic, but it doesn't have no seismic on it. And they received an approval to design their shear walls for an R of 3 for the seismic component. And obviously for wind design, it's just a strength-based design meeting the required strength of the wind loads. So that's kind of ongoing work for CLT shear walls in what you might call the traditional CLT shear wall, because it's kind of hard to call something traditional when it's not adopted in the code yet here in the US. But that's kind of the, here's a shear wall that's kind of just screwed and clipped down, as a typical shear wall is to meet code requirements. There are other kind of innovative CLT shear wall projects undergoing. There's several design projects and researchers around the country looking at rocking shear walls. So take a CLT wall, put a rod down the middle and post-tension that so it's kind of held down by, if you imagine, the rubber band going down the middle of the wall, and then under seismic loads it rocks back and forth but restores itself back into a vertical position at the end of the seismic event. Now, this system has an advantage of really being a low damage system, a resilient system, if you will, where most of our code compliant seismic systems are intended to provide life safety to the occupants, but there could be significant damage to the structural system after the earthquake, which may or may not be economically repairable. The rocking wall system is intended to be a higher or a lower damage system that can be designed for design level events to have very little damage to the actual system itself, and to be kind of more resilient and more rapidly occupiable after the big one. So these are pictures of researchers that, well, low damage. Well, yeah, this is the crushing of like the toe of the wall at 9% interstory drift. So if you're testing something, you test it until you really do damage it. But the intent of these is to be designed for low to no damage under design level or earthquakes. This particular system, the rocking wall system, is the one that's being used on the framework project that is under design in Portland, Oregon. So this is one of the winners of the U.S. Tall Wood Building Prize competition. It's a 12-story tall project, residential occupancy on the top 5 stories, offices on 4, and kind of retail and open, mixed office on the bottom levels. So 12 stories tall, about 130 feet tall, under design in Portland right now, and nearly getting their permit. I think they're planning to start construction later this year, but getting close to their permit. So in that system, they're using this post-tension rocking wall concept to really create a low damage building under the earthquake design events. So we're really, this rocking wall system is a way to not just meet code, but through alternate means and advanced analysis, really go beyond code to create a low damage seismic system. Okay, Marcy, I think we have the next poll. I'll read out the last poll here we have for us. Lateral force resisting systems which have been used with CLT floors and roofs include CLT shear walls via alternate means, wood structural panel sheath shear walls, steel brace frames, or all of the above.
All righty, here we go. People are ready, so they are voting. That's awesome. There seems to be a consensus, so that's good. So they're listening. And I'll give about 10 more seconds. We've got about 75% have voted, so just a few more. All right, I'm going to go ahead and close and sharing. All right, so 95% of you say all of the above, that lateral force resisting systems have been used with CLT floors and roofs. And then just a smattering say the rest. So I'm hopeful that 95% of you are right. So
yes, they are. They are. As a new product that's becoming, more and more designers are becoming familiar with, and architects and engineers, really, pick and choose what's right for your project. It doesn't mean, well, if I want to use the CLT on this project, I have to use 100% CLT. Really pick and choose what makes sense for you and the project at hand. The framework project, 12 stories tall, CLT rocking wall, great, exciting project. They're putting some work into design that lateral system. The Brock Commons up in British Columbia, that's 18 stories tall. They put a lot of work into the kind of the fire resistive design, but they decided to go with a concrete core and not dress that. Vancouver's another seismic region, so they said, well, for our seismic force resisting system, we're going to go with a code accepted, concrete core and not, take off that bite for this new tall wood project. So all of these can be used. They have been used. Okay, So that's the vertical lateral or seismic force resisting systems, which are shear walls, etc. And they're talking about horizontal lateral seismic force resisting systems, which is a lot of words just to say, our floor diaphragms, our roof diaphragms. Again, our actual panels themselves are very stiff and strong, and it all comes down to connections. And if you start to get into the kind of these mass timber designs and these mass timber products and CLT design, really spend some time understanding the different connection technologies and their behavior. There's been some real interesting testing done at different universities around the country and around North America. I'm going to show some graphs here from some tests at University of British Columbia using some proprietary connectors, testing the different panel-to-panel connections. So really looking at that diaphragm shear behavior from panel-to-panel behavior and what that looks like. And if you take two pretty much the same screws and put them in the connections in different ways, you get different behaviors. And if if you just take our spline, and they show these kind of splayed at angles, but if you just took those screws and drove them in vertically or vertically up and down, so that when these panels shear relative to each other in and out of the plane of the screen, those screws are in dowel bearing action. That's very much different if you took those same two screws and skewed them, if you will, in and out of the screen. So when that shear plane starts to move and that those panels try to shear against each other in and out of the plane of the screen, those screws are in tension and compression, not just pure shear dowel bearing. Those are very different behaviors, and those same two screws respond very differently depending upon those. So it's not real, rocket science, if you will, but as you start to use these new kind of CLT panels and start to look at the connections of them and look at the fasteners, kind of make sure you spend some time getting your head around how do these things behave. So if we take those first two, this is the actual testing data from the UBC work, and look at this connection here, and these screws are in pure dowel bearing for the shearing between the panels, and you get a connection that's very soft relative, but very ductile. Kind of has a softer start on the force deformation curve. So this is kind of the displacement to the right and the load going up. So it's kind of our force displacement curve in metric units, because they're up in British Columbia. But you can imagine just the behavior of that connection with those screws and dowel bearing, is not very stiff, but once it starts to engage and kind of get some wood crushing, it has a very long tail, if you will, on the displacement and how much deformation capacity there is, or how ductile that connection is. If you take basically those same two screws and put them in through the half lap condition, but you're still just behaving in that dowel bearing, you're not engaging those in a tension and compression component, you're still remaining in dowel bearing of those screws, because you have a lot more wood that you're connecting to up at the top. It's not a inch plywood spline, it's now 3 or 4 inches of CLT. You have it's much stiffer and much stronger, but you do have you still have lots of deformation capability or lots of ductility in that connection. If you take those same two screws and place them so that they're when that shear force occurs, one of the screws is in compression and one of those screws is in tension, you have a much stiffer connection. So that's this this light green line here. It's a much stiffer connection. It's a much stronger connection. But once you reach its ultimate capacity, there's not a lot of ductility left. So really, depending on what you want to do, you can use those same two screws and get a different behavior out of that connection. Similarly, if you use just kind of a butt joint between the panels, and these screws are skewed both in the plane that you see here, but also out of plane, so that they're receiving tension and compression loads to that shear force applied, again, you get a very similar kind of very stiff, very strong, but not very ductile connection. So kind of bringing this up because it's a real important thing to learn about as you get into detailing these connections, is understanding how the arrangement of those screws can give you very different behaviors. And it's not just, this screw or this nail is worth this strength, but how are you putting it into the connection and how are the loads being transferred through there. So that's kind of the connection aspect just starting on the connection aspect of diaphragms, there's a good document published by Chris Spickler and several other authors that really walks through a design example for CLT diaphragms. This is a great resource that kind of walks through an approach to design these diaphragms. You know, as most examples do, they just kind of picked out a standard kind of floor plan and a standard and a assumed layout of the panels, and then walk through the design process for that. You know, so that's a really good example to walk through to look at the diaphragm design. And it covers both wind and seismic design and gives different recommendations on kind of detailing aspects of diaphragm design. One of the questions that often comes up when designers start looking at CLT diaphragms is it a rigid diaphragm or is it a flexible diaphragm? You know, for a lot of the projects and buildings that we design out there, we really, you know, look at our, you know, concrete floor system is rigid. Our wood structural panel floor system is flexible. You know, the IBC and ASC 7 give us kind of prescriptive ways to assign many buildings to flexible or rigid automatically. But obviously those prescriptive ways of assigning something to flexible or rigid don't apply to a CLT diaphragm. So really, you know, one of the fundamental aspects of CLT design, CLT diaphragm design, well, is it rigid or flexible? Can I classify as one of those? An important component of that white paper by Spickler et al. Was developing a diaphragm deflection equation based upon what we're used to for wood structural panel diaphragm deflections. They've used the 4-term equation, not the 3-term equation, but really it should be familiar to those of us doing light frame wood structural panel diaphragms, where we have the 4 terms of the deflection: chord flexure, panel shear deformations, connection slipped, and chord slipped. And the only one of these that really varies from what we're used to seeing for light frame diaphragms is this connector slip term, really because the derivation of the connector slip term in our light frame diaphragm deflection equation is based upon a typical 4-foot by 8-foot panel. You know, if we look at these CLT floor diaphragm systems, they're not typically 4 foot by 8 feet. They might be 8 feet by 40 feet or some other dimension. So that connector slip term needs to be modified for the geometry of the panels used in our CLT diaphragms. And in that document you'll find this relationship here where this coefficient on that connector slip term is a function of the panel sizes. Really the rest of the terms are similar to what we use for light frame wood structural panel diaphragms. You know, the E sub n is the connection slip at the edge of the diaphragm. We have chord slip, which may or may not be prevalent in our design itself. You know, the panel shear terms, you know, is really just the panel stiffness, and that will be something that you can get from the manufacturer. And then our chord flexure is our typical chord flexure component. You know, what's the area of the chords and what's the stiffness of the chords? How do they contribute to bending of that diaphragm? It's this equation is a great starting point for CLT classification of a diaphragm as flexible or rigid. And if you're not familiar with those different ways to calculate a diaphragm as flexible or rigid, you know, feel free to contact, you know, myself or AWC for the pointers and the standards on where to find those routes to calculated flexible or calculated rigid diaphragms. But it's a nice way to approach it, you know, and if you have a fairly regular, simple diaphragm, I definitely recommend going that route. Let's see. So, but, you know, if you have a very complicated diaphragm, you know, that's complicated could be many different things. You know, there's other ways to go, kind of more refined modeling of CLT diaphragms. And I don't recommend this for every project. It's definitely, you know, work compared to a hand calculation if the hand calculation works. But there's different ways you can approach kind of more detailed diaphragm modeling of CLT diaphragms. You know, you can look at the panels and say, well, these panels are kind of roughly rigid, but, you know, they don't have to be exactly rigid. And you can model the connection stiffnesses between those and come up with a model that explicitly handles kind of the different panels and their configuration. You know, this is something that I've worked with several projects on, and we looked at calibrating kind of our FEM models, if you will, to the calculation, the hand calculation method. And so it's a pretty good matching, and you can get pretty good calculations of deflections really based upon the first principles of the properties of the panel and then what you know about the connections themselves. So for example, I worked with the KPFF team on the framework project. This is kind of a typical floor plate of their system where we have 8 rocking walls around the core. These are on the exterior at this end, but then 6 around the core. And then, on that we have kind of cantilevered diaphragms in this direction, going to the north and south on the plan. So in the east-west direction, this is kind of a cantilever or over 2 support points. In the north-south direction, we don't have those cantilevers, but we have the multiple support lines. And so with the cantilever and the different configurations here, we decided to kind of do the little more complicated diaphragm modeling. Another objective of the KPFF framework project is not just have a low damage vertical force resisting system, which is the rocking walls, but really have a low damage system across the board. So we really designed the diaphragms to a design load that was well above the kind of the minimum design load for diaphragms that you find in ASC 710. And we have 2 holes in the middle, so that kind of complicates the behavior, but that's not atypical, let's say, of an office layout. So won't bore you with all the details, but we really went through here and did a model of every panel, if you will, of every beam that was kind of dragging load, and kind of created these models of how that all came together. And this is the best part of this project, is this nice, pretty, heat map of, if you will, of the deflections of the diaphragms. So this is under about a 0.8 G load, and this is deflections in millimeters. So if you remember, it's about 22 or 24 millimeters per inch. Anyways, this is a little over half an inch, maybe 5/8 of an inch of deflection at the edges of this diaphragm to a design level earthquake event, which created about a 0.8 G load on this diaphragm. So something well above our design minimum loads from ASC 710, but this was really done this way because they wanted to create a diaphragm which really remained essentially elastic under the earthquake and really we'll see little damage. So that's the intent of this design, but it was a good exercise on how to go through the diaphragm modeling and learn how to do this more complicated diaphragm modeling. We have a publication really covering that example design and that example modeling that you can get from the Woodworks website. There's also a World Conference on Timber Engineering paper on that design, but the publication from Woodworks is really a prettier version, if you will, of the World Conference on Timber Engineering paper. And as Michelle mentioned, there are some different structural design articles in the Structures magazine on CLT, so those are good educational documents. Reading 3 documents that are 10 pages long is definitely a better introduction than going and downloading the 500-page CLT handbook and trying to read that front to back. So we have about 15 minutes left, so that's the end of my presentation, or my portion of the presentation. I think Marcy's got some logistics to do, and then we're going to come back for some Q&A.
I do indeed. All right. Let me take the presentation back. All right. So make sure I've got it clean. All right. So everybody's seeing my screen. So, all right, thank you, Scott and Michelle. And as Scott said, I have just some quick information. Our partner organization, Woodworks, thanks, Scott, provides wood project assistance and other resources. If you want to reach out to them, email help@woodworks.org or visit their website at woodworks.org. I'm sorry?
I'm not seeing the slide fully. It's got something over it.
I'm so sorry. Still?
It's good now.
Oh, I thought I was clean screen, so you shouldn't have had that. I apologize. So if you want to reach out to them, their information should be there on the bottom. You can request assistance. Also on our survey, we have a slot where you can request assistance from them. All right, and then our design professional membership, there's information there of benefits that you get. It's just a mere $100. Lots of benefits, including discounts on our publications. Then we have a special Code Official Connections program for our code officials. We'd love to have you join that. There's lots of benefits associated with that program as well. Then a quick reminder that give us about a half an hour to run our reports, and then you'll get an email from us. This does not have your certificates or CEUs. Give us about 2 weeks to run that information and give that get that out to you. Check the email for a survey. We'd appreciate it if you'd fill that out, and that will also give you another chance to win a free publication. Remember that in order to receive your credit, you must have been present for 90% of the 2-hour webinar today. That's 1 hour and 48 minutes. Join us again in May for our header design webinar. And also remember, we have our e-learning program, which you can find in the education section of our webpage. Convenient way to get your CEUs and get more knowledge. If you want to book a live presentation, just contact us. Or if you have any other questions or want more information, just email us at education@awc.org, or just visit our website at www.awc.org. And thank you once again for your attention. And now back to Buddy, Scott, and Michelle for some question and answers.
Okay, great job, Scott and Michelle, and we did have quite a few questions come in. So I'm going to toss it to Michelle first. She's had a little time to read through some of the questions while Scott's been presenting. So Michelle, there were some questions about cost comparisons. Can you address some of those, please?
Right. First, I'm going to show my screen. And there is some information, and I know this is on the Rethink Wood website. There is some case studies that go over cost information, and also on the Woodworks website where they have case studies. I'll go to that, woodworks.org, and Scott can lead you to this also, but I just have it readily available. This particular one is on the Redstone Arsenal that provides some information related to cost, comparing what a typical hotel would be versus the Redstone and the percentage difference. But definitely contact Woodworks because they can provide you with additional information on cost. But it really is not just a materials to materials comparison. One has to take into account the construction, because when you're dealing with a prefabricated product, there's a lot of time that's saved in the construction. So we're understanding the full aspect of the project, not just a material to material comparison.
Excellent.
Yeah, thanks, Michelle. To add that a little bit, it's definitely not just material to material, because I think some people are used to estimating for light frame, and they look at the light frame material costs and double that as their, or as their labor and material costs, and that ratio doesn't apply to like a CLT system. But also, if you're comparing to a concrete or steel system, if you just compare the steel frame to the concrete or to the CLT frame, you're missing the cost benefit in lighter and smaller foundations under the CLT versus under the steel or concrete. So it's not, you really have to get beyond the material versus material, because there's so many other benefits beyond just, the material cost.
Great point. Michelle, another question about how we run mechanicals through or around these systems.
Yeah, I actually have some pictures, because it's similar to all other projects where you're working closely with the MEP to determine where they're going to run their mechanical. If you're dealing with other types of buildings, we want to get this ahead of when it's out under construction. But this is an example of a CLT project where they actually furred up using plywood and ran some conduit through there. Or there's, let's see, I had another picture here where, depending on the system, I can't get it, here it is, that they actually framed it such that they had the allowable area for the ducts to run through. They also fur out walls. Now the capacities of the CLT panels are also pretty good. There's a lot of capacity in there, so they can go through the panels as well, working with the architect. Or some manufacturers may even provide some areas for the conduit and other MEP to go through. And Scott, you may have some additional information on that too.
No, I think it's a good question, and I think you covered it pretty well. It's just you have to work with the system and figure out where to put it. It's not a a cut and dry replacement for a light frame system. If you're doing a concrete frame, you have to figure out where your MEP goes and how they duck around beams or go over beams or through beams. It's kind of a similar kind of design approach.
Scott, next question I'll toss to you has to do with the rocking wall system, and what's the purpose of post-tensioning in the rocking wall?
Yeah, good question. I mean, the post-tensioning in the wall is, and I don't, I guess I wasn't going to show my screen, but I wasn't going to go find the slide. But let me go find the slide.
I did that.
There. In the rocking wall system, there's some sort of shear key to take the shear forces out across the bottom, but there aren't the traditional hold downs at the ends. So instead of those hold downs at the end, which are relatively stiff relative to this post-tension rod down the middle, this post-tension rod really is thin enough, if you will, of a steel rod that it can flex elastically under the earthquake load, but still have that, because it stays elastic, pulls it back together. So the post-tensioning rod down the middle really pulls that wall back together and back to straight up and down after the shaking occurs. So really you get lots of swaying in the earthquake, but no damage to the shear wall, and it's self-righting. It kind of puts itself back to vertical at the end.
Great, thanks. Michelle, next one to you about the CLT handbook, and folks are wondering where to get that, and maybe talk a little bit about what's now incorporated in the NDS and versus the CLT handbook.
Sure. You can obtain a copy of that. Are you seeing my screen now?
Not yet.
Or okay, I guess I didn't get it back. But if you go to rethinkwood.com, not .org. No, I got the screen back. We have here, and if you go to Tallwood, you can get the CLT handbook here. And it's free. You've got to fill out all this information. But that's rethinkwood.com. Now, you should note, though, that the NDS, the 2015 NDS, supersedes the design criteria for, or methodology for, or provisions for what's in the cross-laminated timber. But certainly it has a lot of information related to other than the structures, such as vibration, such as manufacturing, lifting, sustainability, acoustics, a lot of other information that's available.
Okay, great. Thanks. One more to you, Michelle, and then I think you said you had a question for Scott. So talk a little bit about Woodworks software and what we learned from them about their plans for this is the Woodworks software as opposed to the organization Woodworks that Scott is with.
Right. This is Woodworks through the Canadian Wood Council, and they're currently working on a Canadian version to incorporate CLT design. They will eventually do a U.S. version also. There's a Nordique already has CLT in their custom version of Sizer, but this will only cover gravity, not lateral loads.
Then what was your question for Scott? I think you said you had one for him.
Oh yeah, so Scott, related to the lateral design and CLT buildings, what would be the approach for a wind governing type system where seismic isn't a huge issue?
Yeah, that's a good question. Wind resisting systems, for light frame, we typically go to the special design provisions that AWC publishes. So we're still in that situation where CLT shear walls and CLT diaphragms won't be covered there. So you're really to design a CLT shear wall and diaphragm for a wind application where you have really no location with no seismic. You're really going back to first principles, determining your loads, doing your connection design to handle those loads. And you may run into since it's not a code recognized system, it's still a first principles based approach that you can take that doesn't have the complexities, if you will, of seismic design, because you don't have the R factors and everything else. You really can just do kind of a load and capacity based design for wind to handle that.
Yep.
Okay, there was another question about how to handle shrinkage. Either of you want to tackle that, wood shrinkage?
Yeah, I can start with that. First off, when CLT is manufactured, they're drying all the laminations in the wood down to about 12% before it's being manufactured. So as long as that wood stays fairly dry from the point of manufacturing to construction and close-in, your equilibrium moisture content in many parts of the country is somewhere between like 8 or 9% and 12% moisture content. So as long as you're not really soaking that CLT during construction, you're not going to have a lot of shrinkage because the moisture content starting around 12% to begin with. However, if it's something that you really want to think about because you're going tall with it, and you think about it, and you have walls landing on floor plates, and so you're thinking about that and how that occurs, you do the typical calculations you would for wood shrinkage and kind of detail it in a normal manner, but the magnitude is pretty well mitigated because of the moisture content at the time of manufacturing. Now, if you're going to 12 stories or 18 stories like the framework or Brock Commons, you're really not going to want to use a gravity system where you have columns landing on floor plates, resting on columns. You're really going to want to provide a stiff element through the floor zone instead of having the floor plate itself taking that load, not just for shrinkage, but just for load carrying capacity reasons as well.
Great. And Michelle, if you have any follow-up to that, and also maybe talk a little bit about whether preservatives can be used with CLT. There have been several questions about that.
Oh, you were talking to me.
Yes, Michelle.
Yes.
Michelle.
Hi. Yeah, I think Scott covered that regarding the shrinkage issue, and then related to preservative treatment, there are ways to get around that. One is, or durability of the panels is, one is the building envelope itself protecting the panels, but another is that there could be the case where you have treated wood covering the wood cross-laminated timber, but you would really have to work with the manufacturer to see if they provide that as a product with a treated wood on the exterior.
Yep, good call.
Yeah,
and go ahead.
Just to add to that though, is that the PRG 320 product standard does not cover exterior exposed CLT. So in those exterior exposed applications, you're kind of outside the scope of that current product standard. However, there are CLT manufacturers who have experience in creating CLT for exterior exposed conditions, and even untreated ones and untreated wood. And last summer I was on a tour in Europe and saw many building examples where they had CLT exteriors on the building, untreated wood, and it weathered and it grayed, but there was not an issue with the adhesives or everything. It was more of just an appearance issue, whether or not that graying, if you will, was acceptable. So it's outside the scope of the standard right now, but if you're interested in something like that, there's definitely the manufacturers who would be willing and interested to talk to you about the possibilities.
Okay, and so I think the last question, Michelle, there was somebody just wanted to follow up about whether CLT is accepted in the 2015 IBC. So if you could address that one, and then Scott, I'll toss the last one to you about manufacturers in the U.S. So
yes. Okay, CLT is adopted into the 2015 CLT. If you have a printout of the actual presentation, there are slides that cover that in the beginning of the presentation on where it's adopted in the 2015 IBC.
Great. Scott, can you talk just briefly about some of the manufacturers in the U.S.?
Sure. Well, there are 4 manufacturers in North America that have been certified to the PRG 320. Those are, one's in Oregon, one's in Quebec, Canada, one's in Montana, and one's in British Columbia, Canada. So there's 2 current manufacturers certified in the U.S., 2 in Canada, and then kind of a split between the East and West. Now, there are many more possibilities coming online over the next couple of years, but those are the ones who are certified right now. And there are other manufacturers who are actually manufacturing CLT already who have not yet completed the standard, the certification. But right now we have Oregon, Quebec, Montana, and British Columbia as locations of North America manufacturing.
Great. Well, that's all the time we have for today, folks. Thanks for tuning in. And Michelle, Scott, thanks again to both of you for a great presentation, and hopefully we'll see you all again next month. Have a good day.